thank you very much for the kind introduction, and thank you for inviting me to this Peter Spin workshop on topology and magnetism and ferroelectrics. So here's the outline of my talk. I'm first going to give a short introduction to topology and actually how different magnetic textures are related to each other. Then I'm going to give a brief intro into the Skermion Hall effect, which we already have seen in the seminar series, but towards the goal of the question how we can eliminate the Skermion Hall effect and how we can then use two techniques to eliminate the Skermion Hall effect to actually find a non-zero Skermion Hall effect for topologically neutral magnetic structures. So in particular, the last part of the talk was done in collaboration with Robin Misiska, David Rodriguez, who's now an assistant professor at the Politecnico di Bari and who's also in the audience, and Jonathan Lilliard. So let me start by topology. In topology, one wants to know if structures are topologically equivalent, and probably most of you know this cup to donut video, which you can find on Wikipedia, and this version was done by my PhD student, Ross Knappman. And once we go towards magnetic structures, or more generally structures that are characterized by a vector quantity, then we want to know if we still continuously deform them into each other. So while you can try to find such a mapping by finding out how you can deform them into each other, there's another concept that you might use, which is the concept of the order parameter space. So in the first part, which is a topological trivial structure, everything is like ferromagnetic, all orientated at one. If you map this to the order parameter, every spin or every vector is looking towards the same direction. For the middle one, you can start from this vector and map it here to the order parameter space. And when you follow it across the ring here, then you're going to find that you first twist towards the right, but then back towards the left and then back again. So finally, you didn't go around this ring. While when you just follow it for the last texture, then you actually go twice around with the angle. And similar as here, you can just compute a simple index, which is the number of holes. You can then, for magnetic structures or for vector quantities, something that is a topological index, which in this very simple case is just the winding number. And what you need to do for this in this one-dimensional part is just add up the change of the angle and then sum it. And you divide by 1/2 pi to get an integer. So if you look at it from a mathematical point of view, we are dealing with a homotopy group theory, which is pi1. We go one-dimensional closed path and we map it to an order parameter space that is S1. And this means that we get Z. So every time you can wrap around a ring an integer number. And you get minus the winding number, of course, if you go the opposite way. If we now look at magnetic Skermions, then we have already seen the mapping to the sphere. So here we are dealing with the homotopy group pi2 of S2, which also tells us that we can map an integer number to the sphere. And what we now need to compute is not just the change of the angle, but the two-dimensional version of it, which is then the solid angle. So you can try to convince yourself that this winding number is nothing else than the summation of the solid angle and divided by 1/4 pi, because that's the volume of the surface of the sphere. So interestingly, there's a connection from a domain wall to a Skermion. So if you start with a domain wall and then just extend this domain wall into another dimension, then you can get a Skermion by just combining this domain wall to a ring. And now the same concept that we have done, we can just do again. So in case you couldn't follow the movie, here's just a short image sequence of how you can just bend it towards a Skermion. But now we can do the same concept again. We can start from the Skermion. And now I'm just gonna enlarge the movie a little bit so you can start from the Skermion. You can put it into the third direction, so extend it towards a string, maybe twist it, and then bend and connect it together again. So thereby you can go from a domain wall to a Skermion over to a Hopfion. And in 3 dimensions, you might easily appreciate that you can do a lot more things, because you can not only twist the string, but you can also form knobs. Therefore, you get lots of different Hopfion structures. So going back to homotopy group theory, you get pi2 of S2 for the Skermion, which is an integer, which I already explained before. And here we sum up the solid angle, but we can just put it for the Hopfians, as we have seen that for a very easy way, we just get a cross section of a Skermion in a Hopfian into a more general notation by expressing this as a vector quantity for the third component. And the more general vector quantity is this F alpha here, where you just don't say that your structure is in a plane, but you allow for all different indices, X, Y, Z. And then the Hopfion itself has the homotopy group pi3 of S2. So you still have angles, but you go a three-dimensional closed surface, which is the torus, or more general structures. And the Hopf index itself now uses this F, or is like, and also some parts of the curvature, which then explains you why this one also gets you an integer. So as Berger already nicely explained in his talk, there is a difference between math and physics. So in math, we look at continuous vector fields. And in physics, at some point, at least on the size of the atoms, we become discrete. So therefore, in math, you can say that topological sectors are really distinct, and there's no way to go from one class to another class. So they are really topologically protected. While in physics, sectors with different topological indices are separated by a finite energy barrier. We can create and destroy, for example, Skermions, and therefore it's probably better to talk about topological stabilization. And there's another very interesting concept. So when introducing these homotopy groups, then what was very important was the dimensionality. So in math, we have very fixed dimensions, so it's 1D or 2D, but in physics, we can start to grow more layers on top of each other, and we go from 1D towards 2D behavior by just building wedges. And of course, similar things one can do going from 2D to 3D. So therefore, we have a bit more playground, and one needs to look at things a bit more differentiated when talking about topology. So let me now come to a short introduction to the Skermion Hall effect. So for this, it's good to have an overview of which type of forces are acting more or less in general on, for instance, a Skermion. And I would say that there are basically three types of forces when looking at current-induced magnetization dynamics. One of them are pinning forces, because if you just the drive that you apply is not large enough, your magnetic structures are pinned. The second one are dissipative forces, meaning that what you feel when you are on a boat in a river, that you're just dragged along with the current. And the last one are the ones that are called Magnus forces, and which became famous in this field as the Skermion Hall effect. So for Skermion lattices, they have been found already quite early on, and for single Skermions, they have also been the Skermion Hall effect at least now 6 years ago. So let's look a bit into this into detail, and actually what is the role of topology now in the Skermion Hall effect. So recently, Jan Marcel, who's I think also in the audience, and I have written a bit of a book chapter to also express this a bit in a more overview style. So let's look at the simple structures. And if you want to know more details, I just refer you to this article. Then we can look at the LRG equation. And what we have here in the end are torques, and very famous ones are spin transfer torques and spin orbit torques. If you just compare these two terms, then you see that spin transfer torques are acting only when you have a gradient in the magnetization, meaning that they only apply to magnetic structures. Spin orbit torques, however, don't need this gradient, so they would also act on uniform magnetic structures, so like ferromagnetic ones. So let's start with spin transfer torques. And let's do a Thiele analysis of a rigid moving structure. So just saying that our magnetic structure moves with a certain drift velocity. So if we take this approximation, then we can derive the equation of motion of this rigid moving structure, which, by the way, does not have to be a Skermion. I just plotted the Skermion here because it's nice. But we get an effective equation of motion, which shows us the forces that I've mentioned before, which are pinning forces, dissipative forces, and then these Magnus forces, which are like perpendicular for any rigid structure. If we now neglect pinning for the moment, then we can put here 0, and then we can really look at what is the role of topology. So where does topology enter? If you just consider a two-dimensional magnetic structure in the xy plane, then this gyro vector just has a 0, 0, and then this W here, which is the Skermion winding number. So if the Skermion winding number is 0, then obviously the drift velocity is along the applied electric current. So just from this equation, we can compute the Skermion Hall angle. And if we just study this Skermion Hall angle for a moment, then obviously we see it vanishes for structures with Skermion winding number being 0, as it should be. But we can also see that the only thing that enters is really the winding number. So it does, for instance, not depend on the helicity of the Skermion, whether it's Neil or Bloch or any twisted type of structure, or whether it's really like any different angle. So, and it also changes the sign when we just revert the sign of the winding number. So it just is an odd function in the winding number. So this tells you a recipe how to eliminate the Skermion Hall effect. You just take one Skermion with a positive winding number and one Skermion with a negative winding number. If you apply current, each of them would feel Hall angles, but just in an opposite direction. If you now strongly couple them, then they are coupled and these forces that act in perpendicular directions just cancel. So then you get rid of the Skermion Hall effect. So basically there are three different ways to have, in a sense, this strong coupling, and Berger has mentioned them already. So one is that you create synthetic antiferromagnets, meaning that you have bilayer structures with oppositely oriented magnetization directions. You can just merge the two Skermions fully, thereby you create an antiferromagnetic Skermion, or you can just open up one Skermion and put another Skermion in the center, which has the opposite orientation, which is called a Skermionium. So now we have looked at spin transfer torques, and here the winding number is really crucial, and we only get a Skermion Hall effect when we have a topologically non-trivial structure. Let's look at spin-orbit torque physics now. We can do a similar Tidal analysis for the Skermion, and then we get the spin-orbit torque, that spin-orbit torque Skermion Hall angle, which looks like this. So first of all, it does not simply change the sign when we put the winding number to minus the winding number. Second, there is this eta here, which is actually the helicity of the Skermion. So it does depend explicitly on the helicity of the Skermion. And let me just remind you about helicity. So helicity is this in-plane angle. And in our choice of coordinates, it's 0 for a Neil Skermion or pi, and pi half plus minus for a Bloch Skermion. And anything else in between can, of course, also happen. So this gives you another recipe how to eliminate the Skermion Hall effect. Namely, you can just tune the helicity such that the spin-orbit torque Skermion Hall angle vanishes. And let me also remind you that because of this, when changing the sign, it does not simply change the sign of the Hall angle. We actually have a sort of an asymmetric Skermion Hall effect. So let me explain this asymmetric Skermion Hall effect for twisted Skermions a little bit more in detail. So when you have a Neil Skermion and you apply current, then actually you get a certain type of Hall angle. And for the opposite polarity, so blue is now on the outside and red is on the inside, then actually it's just the opposite angle. So it's symmetric around the current direction. But when you start twisting your Skermion, then this is no longer the case. So for one Skermion orientation, for one polarity, it gets suppressed. and for the other, it gets enlarged for the opposite polarity. So thereby you can have no Skermion Hall effect for one polarity by tuning the helicity. So how can one see that? So actually, without any details of the magnetic structures, you can just start from a twisted Skermion, and by a rotation of the spins, you can bring it back to a Néel Skermion. So we just do from the lab frame a rotation into a rotated frame, and now we can look at how the equation looks like for the rotated frame. So what we see is that we actually get a very similar LMG equation as the one in the lab frame, but of course with some changed torques. So instead of the lab frame where we have a tilted Skermion, some torques acting and a current, we now have a Néel Skermion, but modified torques and potentially a modified current. So the consequence is that all torques that are covariant under the rotation have the same dynamics as Néel Skermions. So as a result, what we find and what I already discussed is that for spin transfer torques, this is the case. So twisted Skermions behave the same as Néel Skermions, so the helicity does not enter. But for spin orbit torques, actually the twisted Skermions behave different to Néel Skermions. So they feel an effective current, which is just the rotated normal current. So you can see that the equation for the torques is very, very similar, besides that here now we have a tilde, so a rotated current. So with that, we can complete actually this figure here by just adding here the effective current that the twisted Skermion is feeling, around which it's actually again symmetric. So still the Skermion Hall angle, which is the direction of the current with respect to the moving of the structure, is then suppressed for one polarity and enhanced for the other one. So this has also been confirmed by numerical simulations by Nico Kerber and Jonas Nothelfer. So I have now basically discussed two different strategies how to eliminate the Skermion Hall effect. So one was using spin transfer torques with the idea that you take two Skermions that are opposite, or two magnetic structures that are opposite in their winding number, and therefore the perpendicular forces cancel. And the other one is using spin orbit torques and an additional symmetry breaking. What is really interesting is that you can combine now both techniques to eliminate the Skermion Hall effect, to get then a non-zero Skermion Hall effect for topologically neutral magnetic structures. So in a sense, you do 0 plus 0 is not equal to 0. So I'm going to show you now that you can obtain a non-zero Skermion Hall effect for topologically neutral magnetic structures. So this is work, as I mentioned in the beginning, that has been done by Robin Lisiska, David Rodriguez, and with Jonathan Lilliot. So one idea was to have two strongly coupled Skermions with opposite winding numbers, where the force components perpendicular to the current cancel each other for STTs. The other one was that for SOTs, that's not the case, and we get this asymmetric Skermion Hall angle. So if we combine these two ideas, namely we use a strong coupled Skermion system with opposite winding numbers and spin orbit torques, then we get a non-zero Skermion Hall effect, even if these topological indices, the individual ones, cancel. So this strong coupling you can, as I mentioned before, obtain in three different ways. So one is synthetic antiferromagnets. And here really the idea is that the force that is acting on the top Skermion is, for instance, smaller than the one acting on the bottom Skermion, and thereby you still get the Skermion Hall effect. You can do it for antiferromagnets, and the picture is just the same. So the effective force acting on one of the sublattices is smaller than the other one, and they don't cancel. And last but not least, you can do it for the Skermionium, where then the force on the inner one is then smaller than on the outer one, or vice versa. So, and very interestingly, for the Skermionium, it's even a non-zero Skermion Hall effect for a topological trivial structure. So for the other two, I would rather call it a topologically neutral structure, meaning the idea that you have two individual Skermions and they can bind their winding numbers together. But for instance, for the antiferromagnetic Skermion, you can also define the nail vector, and then based on the nail vector, you still find some topology. But for the Skermionium, you really have then a topologically trivial structure where you don't find a Skermion Hall effect, a non-zero Skermion Hall effect. So let's look at this. And one very interesting part is that you can treat all three systems with the same theory, with the same Sila analysis, so synthetic antiferromagnets as well as the Skermionium, by just considering as two different radii, so two Skermions with two different radii that are then coupled. So for the Skermionium, it's one time the inner radius and one time the outer radius. And if you have a simple two-layer system, then maybe both radius are the same. So one can look at all the different force components acting on the two individual Skermions. And I'm not going to go into detail of this, but I would like to focus on the first row, namely the part where typically the topology enters. So the topology enters in this G, and actually this is now fully gone. So whatever is remaining has then no topology left in this sense. So for the very simple case, one can even get a simple result out, namely for the case of these two radii being the same as one would have for the antiferromagnetic Skermion or for the bilayer system, then you just find that the Skermion Hall angle is just related to the helicity. And it's very independent of the microscopic origin of where this helicity is coming from. So this we confirmed also by the analytics as well as by micromagnetic simulations. So with this, I'm at the end of my talk. I showed you how to eliminate the Skermion Hall effect with at least two different methods. I discussed then how one can combine these two different methods to actually get a non-zero Skermion Hall effect for topologically neutral and even topologically trivial structures such as the Skermionium. And I would like to acknowledge, of course, the funding we receive, thank my team and our collaborators for all the support, the same for my family and you for your attention.